The last test for convergence of series that we're going to discuss will deal with alternating series, which are series of the form that I shown here. So as you remember from calculus, the alternating series basically is a series which has alternating signs. So there is an n missing here. So you have minus 1 to the n. That means that each next term is going to have an opposite sign than the previous term. So if we look at the alternating series like that, the goal is going to be to figure out, is there any way for us to determine whether a series like this converges? So what sort of things do we have to verify to conclude that that alternating series converges? So here we have the alternating series test, which tells us the following. So if we have an alternating series, and of course, at the core of alternating series is a sequence an, a sequence of positive terms. So if the sequence satisfies the following two conditions, number one, the sequence an is decreasing, and number two, the limit of the sequence is equal to 0, then these two conditions will be sufficient to conclude that the alternating series itself converges. So let's try to prove this. To demonstrate that the series converges, we need to prove that the sequence of partial sums of that series converges. So if I denote the partial sums by Sk, sum of the first k plus 1 elements, because I'm starting from n equal to 0. So I want to show that the sequences actually converge to some number, finite number, as k goes to infinity. And I'm going to do this in 3 steps. So on the first step, I will consider a subsequence of Sk, which consists of all partial sums with odd indices. So it will be S1, S3, S5, S7, and so on. So notice that a sum with an odd index k, if k is an odd number, if we add terms from 0 to an odd index, from 0 index to an odd index, then we have odd plus 1 even number of terms. So by looking at S with odd indices, I'm looking at partial sums that have even number of terms. As you also might recall from calculus, if you want to enumerate all odd terms, then you can have L that goes from 0 to infinity, and then you'll march through all odd terms by using an index 2L plus 1. So we're looking at the subsequence of Sk, which consists of S2L plus 1. Okay, so then S1 is a 0th term plus a first term. S3 is the same thing as S1, but also plus A2 minus A3, and so on. I know nothing about this sequence. It can be whatever, this S2L plus 1. So if I have any hope to prove that the sequence converges, then I probably should use some sort of an indirect proof that does not require me to know what the limit is. And so what sort of indirect proof I can have? I can prove that the sequence that I have is a Cauchy sequence, or else I can prove that this is a monotone sequence which is bounded from above or from below, and from that I can deduce convergence. So let's see if anything like that works here. So it's true that the sequence S2L plus 1 is monotone. So how can I decide? I can subtract two consecutive terms in that sequence. So taking some arbitrary term S2L plus 1, what's the next term? That's a term with which you have to replace L by L plus 1. And actually, if I open the parentheses here, I'm going to get 2l plus 3, right? So 2l plus 1 is an odd number. Next odd number is going to be that number plus 2, so it should be 2l plus 3. So I'm looking at the difference of these two partial sums. The first one is a sum of all terms of my series starting from 0 up to 2l plus 1. Second one is a sum of all terms up to 2l plus 1. So 2l plus 1 actually is 2l plus 3, as I said. So in the first sum, actually, that sum contains everybody from a second sum, but it also has two more terms, 2l plus 2, a and 2l plus a, 2l plus 2, and a 2l plus 3. So in other words, if I take a sum that ends at 2l plus 3, and I remove all terms up to 2l plus 1, I'm left with just the sum from 2l plus 2 to 2l plus 3, which is going to give me only two terms. If I substitute 2l plus 2, I get this. If I substitute 2l plus 3 for n, I'm going to get that. Now, 2l plus 2 is an even number. 2l plus 3 is an odd number. So minus 1 to the power 2l plus 2 is going to be 1, and minus 1 to 2l plus 3 is minus 1. So what we got then is a 2l plus 2 minus a 2l plus 3. But the sequence of a's is decreasing. So that means that a 2l plus 3 must be smaller than a 2l plus 2, so the difference is going to be non-negative. Which then tells me that if the next term minus the previous term of s, of a sequence s2l plus 1, is greater or equal than 0, then that sequence must be decreasing. Increasing, right? If the next term is larger than the previous term. So S2L plus 1 then is an increasing sequence. Right, so the thing that might be confusing here is I'm taking the difference between next term in S2L plus 1 and the previous term. And that is equal to the difference between previous term and the next term, but in terms of a now. So this guy is positive because a is decreasing, and so that makes S2L plus 1 increasing. All right, so then if it is an increasing sequence, if I can also show that it is bounded from above, then I'm in business. So to do this, let's analyze the sequence S2L plus 1 in a somewhat different way. The way I can write it is as follows. So it's A0 minus A1 plus A2 minus A3 plus A4 minus A5, etc. And then it will end with these terms. What can I see here is that because an is decreasing, a1 must be larger than a2. So minus a1 plus a2 is negative, is non-positive. Likewise, a3 is bigger than a4, so minus a3 plus a4 is negative. And I can continue like that, and the last three terms, a minus a2l minus 1 plus a2l, again is negative because a2l minus 1 is larger than a2l. And then a2l plus 1 I'm subtracting, so this is negative. So then overall, if I look at S2L plus 1, then I can think of it as a positive term A0, and then everything else can be combined to look like negative terms. So that means that overall, S2L plus 1 must be less or equal than A0. But that is true for all L in N, right? Or for all natural number L. And so therefore S2L plus 1 is bounded from above by A0. And so therefore S2L plus 1 is increasing conbounded, and thus it must converge as L goes to infinity. So that means that the subsequence of a sequence, subsequence with odd indices of Sk, of a sequence of partial sums, this subsequence converges as L goes to infinity. So now let's look at the sequence of even partial sums that contain odd number of terms, again, because we're starting from 0. For example, S0 will have only one element. S2 will have 3 elements, right, because it's A0 minus A1 plus A2. So the series that contains odd number of elements then can be denoted by S2L, right, because we have to pick off even indices. And so let's try to do the same procedure as we did with odd partial sums. Let's take a difference between two consecutive terms of S2L plus 1 and S2L, right? So two consecutive terms with even indices, or two consecutive terms, two consecutive partial sums with even number of terms. So just like before, we have one partial sum that ends at 2L plus 1, another one that ends at 2L. 2 times L plus 1 is 2L plus 2. And so once we remove this sum from the first sum, we're left with a sum that contains only two terms, 2L plus 1 and 2L plus 2. If we write this out, we have two terms still. The first one has minus 1 to 2L plus 1. 2L plus 1 is odd. It's an odd number, so minus 1 to that number is negative. 2L plus 2 is an even number, so minus 1 to the power is positive. It's just 1. And so we have minus a to L plus 1 plus a to L plus 2. Again, the sequence is decreasing, so the negative number then is the sequence n is decreasing. So the previous number is always larger than the next number. Previous number comes in with the minus sign, so this is less or equal than 0. And so that means that the sequence S2L is going to be now decreasing, right? Because the difference, the next term minus the previous term is negative, so the next term is smaller. So the sequence is decreasing, so now we have to show that that same sequence is bounded from below to conclude that it converges. So let's look at S2L. Again, this is just A0 minus A1 plus A2 minus A3, etc. The last three terms are A to L minus A to L plus 1 plus A to L plus 2. So now grouping them in a slightly different way, let's take A0 minus A1, right? Again, A0 is larger, so the difference is positive. A2 minus A3, A2 is larger, the difference is positive. We keep going like that. The next to the last term and the previous term, their difference again is positive because A to L is bigger than A to L plus 1. And then because S to L overall contains odd number of terms, there is an extra guy, A to L plus 2, in there, which is also positive. And so that means that we can arrange a sum S to L in such a way that it just consists of a sum of positive contributions. So overall, S to L must be greater or equal than 0. But if it is greater or equal than 0, then S to L is bounded from below by 0, and so therefore S to L is decreasing and bounded from below, so it must also converge. So the subsequence of all odd partial sums converges, subsequence of all even partial sums converges. But we have a question what the relationship between the limits of these two subsequences is, because if the limits are different, then the series cannot converge. Then the sequence of partial sums cannot converge. All right, so to see what the difference between the limits is going to be, let's just compute it. So the step 3, now I know that this limit exists and this limit exists. So by properties of limits, difference of limits is the limit of the difference. Our usual trick, S to L plus 1 is a sum that ends at 2L plus 1. S to L is a sum that ends at 2L. If I subtract them, then the only term that remains is 2L plus 1 term. That's the only term that is not in the sum that I'm subtracting. So I have only one term left. 2L plus 1 again is an odd number, so minus 1 to an odd number is minus 1. I'll pull out this minus 1 and I have a limit of a to L plus 1 left. But we did assume in the beginning that the limit of an must be equal to 0, so then the limit of a to L plus 1, which will go through all odd terms, there's a subsequence of the original sequence an, so this also must be 0. And so what do we conclude from that is that this limit minus that limit is 0, so both limits are the same. So subsequence of all even terms converges to a number. Subsequence of all odd terms converges to the same number. So it means that the entire sequence just converges. And if a sequence of partial sums converges, that means that the series converges. And so we proved the alternating series test. And let's do a couple of examples of that. So let's look first at this alternating series, minus 1 to the n over n. And I have two questions, actually one question. Does a series converge absolutely, conditionally, or it does not converge at all? So certainly it does not converge absolutely, because if I take a series of absolute values, if I drop minus 1 to the n, then I end up with a harmonic series, and harmonic series by default diverges, as we already proved. So if this alternating series converges, it cannot converge absolutely, therefore it must converge conditionally, again, if it converges. Okay, so because it's an alternating series, I can try to apply an alternating series test. What is an in this case? It's 1 over n, right? Once I remove minus 1 to the n. And 1 over n certainly is a decreasing sequence, and its limit is 0, right? Limit of 1 over n is 0. So that means that the conditions of the alternating series test are met, and so therefore my alternating series converges, and it must converge conditionally because the series of its absolute values does not converge. Now let's look at a similar guy, except that we have n squared on the bottom. Exactly the same question. Now, the series of absolute values will be 1 over n squared, and that's a p series with p equal to 2, and 2 is greater than 1, and if p is greater than 1, then the p series converges. So that means that the circle series converges absolutely, right? Because the series of absolute values converges. And if a series converges absolutely, we proved before, then it must converge just by itself. So to prove that this series converges, I don't need to use the alternating series test. I could, but it makes no sense to use it because I already proved that the series converges by showing that it converges absolutely. So no need to use the alternating series test here. All right, and so that would be the end of this section.